And after that, we'll start with the first talk. Professor Ann White from MIT will start us off.
All right, thank you very much. Thank you very much. I'm very happy to be here and very grateful for the invitation and for this opportunity to present measurements of electron temperature fluctuations on D3D. I'd first just like to thank a lot of co-authors who've participated in this work and also thank the D3D team for supporting these experiments. Now we know that turbulence can play a very central role in the cross-field transport of energy, particles, and momentum in magnetically confined plasmas. And so it's of great practical interest for fusion energy research that we develop and deepen our understanding of the turbulence. And all the talks that are going to be happening this afternoon are going to be describing experimental measurements on the D3D tokamak. Now this is a modest-sized device with major radius about 1.7 meters and minor radius about 0.7 meters. The magnetic field on axis is typically 2 to 2.1 Tesla. The plasmas are run with 1 to 1.2 mega amps of current. The D3D tokamak is flexible, has very good plasma control system, and also comprehensive heating system. So we have and counter-injected neutral beams, as well as RF. Shown here on the left are just some parameters of interest for turbulence in sort of a typical L-mode plasma, where a lot of the measurements of the temperature fluctuations that I'll be showing you were made. Typically, no. I mean, when we run the simulations with gyro, we do them just pure electrostatic and then also electromagnetic as well. We don't see a huge difference. I mean, it's a very low beta plasmas in the L-mode cases. So at D3D, we employ a very large suite of fluctuation diagnostics, which allows us to measure a range of turbulence scales and characteristics. Shown here in this illustration, it seems a little overwhelming at first, sort of just looking at it visually. But it's helpful because we can break down the turbulence measurements at D3D very roughly, maybe into two sections. A first section being we could measure line-integrated information about density fluctuations. Say with a viewing cord for an interferometer radially or vertically. Also line-integrated information on the density fluctuations comes from a phase contrast imaging systems, which has a vertical view. But the fluctuation measurements we're going to be most interested in, I think, for all of our talks are really more localized measurements. And those are coming from a variety of things, like the beam emission spectroscopy diagnostic, Doppler reflectometer, and also the correlation ECE system. And what you can see about the clustering of where these sample volumes are, sort of all on the outboard side here, links back to what Steve was saying in the talk this morning, is that when we make measurements of the fluctuations in the tokamak, generally all of our systems are looking from the outboard side of the tokamak at the midplane in, and we very seldom have fluctuation measurements on the inboard side. Now in terms of what the local fluctuation measurements actually do, all these diagnostics, CECE, BES, and the Doppler reflectometer are tunable. So we can scan really where their tiny sample volumes, which are centimeter scale in size, are looking radially on a shot-by-shot basis. And that's how we build up the information about how the turbulence is varying radially in the plasma. So the fluctuation diagnostics at D3D, again, cover this wide range of spatial scales in the turbulence, from K theta rho s of 0.1 all the way up to 10. Sort of covering regions where we expect turbulence mechanisms associated with ion temperature gradient and trapped electron mode instabilities to be relevant at the long sort of to medium wavelength. And then at the very short wavelength, the very high K scales, you can have the ETG activity, which can be picked up again with some of the diagnostics here. And so even though we can sort of scan and get information on the density fluctuations over this very wide range of K, we can also get information at the lowest K about multi-field fluctuations. And that's really what this talk is going to be focusing on the measurements of the long wavelength electron temperature fluctuations with the CECE diagnostic, and also some of the more recent measurements we've been making with coupled reflectometer and CEC diagnostics to look at the phase angle between the density and the temperature fluctuations. So despite this very wide range of diagnostics, it does give us extraordinarily detailed information about the underlying characteristics of the turbulence. It's important to point out that none of us, not at D3D, I don't think at NSTX or TOR Supra, which are the talks we're going to be hearing tomorrow, even with extensive fluctuation measurements, we don't have access perhaps to the real underlying quantity that we'd like to have to compare with the transport. And that would be none of us really measure the turbulent flux. So instead we rely heavily on models and simulations and workshops like this to try and connect us all together, experiments and theorists, so that we can really interpret what it is we can measure and what this can tell us about the turbulent transport. And so before I get into the details of the correlation ECE diagnostic and showing you some of the experimental results, I just wanted to put up here a quick summary sort of what's coming in the talk. We find that in ITG-dominant L-mode plasmas, the long wavelength electron temperature fluctuations that we measure are very similar in amplitude and spectrum to long wavelength density fluctuations. And these fluctuation amplitudes range from about 0.5% to 2%, increasing with radius. We also find that after the H-mode transition in the core, not just the edge, in the core plasma, electron temperature fluctuations are significantly reduced. And this is attributed to an increased E cross B shearing of ITG turbulence after the transition. We've also found in experiments where we can increase the trapped electron mode drive, and this comes with increased thermal transport using ECH to modify the plasma profiles. We found that the long wavelength temperature and density fluctuations respond very differently. We see significant increases in the one field, the electron temperature fluctuations, and much smaller, really little to no change in the long wavelength density fluctuations. And so this sort of difference in how they were responding to changes in ITG and TEM drive experimentally, we've gone through and tried to look at some nonlinear gyro simulations. And those show us that this increase in transport as we increase the trapped electron mode drive comes along with two things. A large change in T tilde with smaller changes in the N tilde, but also a change in the underlying cross-phase angle between the density and potential fluctuations. Now again, that's something we can't measure, but we can access now a change potentially in the N tilde and the T tilde phase angle. And what we found there is if you use this as sort of a proxy for the N and phi phase angle, we find very good agreement with the predictions from gyro, but here ongoing modeling effort is required. And so this is a diagram of the correlation ECE diagnostic. It measures essentially when we have this magnetized plasma. It's optically thick. It's going to emit at the cyclotron frequency, sort of black body level emission with an intensity proportional to the temperature. Now we can then measure this with a radiometer. And if we have frequency resolved measurements of this emission, by scanning and changing the frequency that the radiometer receiver is looking at, we can scan and move and look at different radial positions in the plasma. And so radiometry on its own has very excellent spatial and temporal resolution and is widely used to measure the temperature profiles in tokamaks. However, a single channel of a radiometer signal is unable to measure low amplitude, 1% level, very broadband temperature fluctuations. In order to measure the turbulence, it was developed sort of in the mid-90s that if you could take two radiometer channels which were incoherent with respect to this intrinsic thermal noise and correlate them, you were able to pick up and extract out the information about the fluctuation levels and spectrum. And so we can make the thermal noise incoherent by selecting two very closely spaced regions in the plasma, by selecting two very closely spaced but disjoint frequency bands to make the measurement over. And as long as these are separated by less than the radial correlation length of the turbulence, when we correlate the signals from these two sample volumes, okay, we're getting that information about the cross-power spectrum of the electron temperature fluctuations and the amplitude. So the sample volume size here for this system vertically is about 3.5 centimeters, and radially it's set by the emission width of this layer, and it's about 1 centimeter. So that places the CECE looking really at the longest wavelength fluctuations in the plasma associated with ITG and very long wavelength TEM. And so this is just a quick slide showing how we can, just showing some raw data, basically the correlation coefficient as a function of time delay between those two ECE signals, shown at three different times during a discharge, L mode and then also H mode. We pick up with standard spectral analysis the cross-power spectrum, and that's shown here in the L mode cases, power plotted versus frequency in kilohertz. And you can see, I'll talk about this in a moment, that we sort of have this strong reduction again as we go from L mode into H mode in the fluctuation amplitude. And it's important to point out that the spectral shape that we measure of the turbulence is dominated by Doppler shifts, okay, due to the background E cross B speeds in these plasmas. And so, looking in more detail at this reduction in the electron temperature fluctuation amplitude we see as we go from L mode to H mode, looking in quiescent H mode experiments, which are ELM-free, has been extraordinarily important, I think, for really pulling out what's going on here. Now you can see the time traces here for these particular discharges have counter-injected beams, neutral beam power coming in here, line average density, central temperature at about R/A of 0.7. This is the edge D alpha light, so you can see the drop as we come along with increased beam power. We transition from L mode into H mode, and you can see the measured fluctuation amplitude here in L mode at R/A of 0.7 is about 1.5%, drops down to below the sensitivity level of the diagnostic after the transition, and remains there throughout this quiescent H mode phase. And so immediately this result gave us a very strong correlation between improved confinement, so changes in transport, and a reduction in this fluctuation level that was measured. And shown here are just the power spectrum in L mode, H mode, and ohmic plasmas at about rho of 0.75 or R/A of 0.75. And you can see the reduction in the fluctuation amplitude as we go from L mode to H mode, and also the changes in the shape of the turbulence spectrum as we have a plasma which is beam heated, so we have some very fast rotation, and we pick up the Doppler shifts, and we compare it to a plasma which has no beams, just ohmic heated. The spectrum is very narrow there in these cases. And so this core turbulence reduction in QH mode again suggested that there could be a substantial contribution to the heat flux in these experiments from the electron temperature fluctuations, because across the radius, when we made the measurement of the profile in L mode and then compared it to the measured profile in H mode, we saw always a significant reduction. And again, this reduction comes along with an improvement in confinement. And so if you plot sort of the chi-E, the heat diffusivity here, as a function of radius determined from power balance calculations, comparing the solid line in L mode to the dashed line in one of the QH mode cases, you see you have a significant reduction in the transport, and you also tend to have an increase in this ratio of the E cross B shearing rate compared to the linear growth rate of the ITG mode. And so the drop in the electron temperature fluctuations as we go from L mode to H mode could be attributed to ITG modes that are being sheared apart by the E cross B flows in the core of the H mode plasma. So this was already a rather interesting result, that we would have sort of ITG turbulence, which very significant electron temperature fluctuations that were roughly the same amplitude as the density fluctuations, but we hadn't yet measured them simultaneously. And so to do that, we wanted to prepare an experiment to let us compare very directly the BES measurements of density fluctuation levels and the CECE measurements of the electron temperature fluctuation levels. So shown here is just a cartoon of where the sample volumes for these two diagnostics are looking. And what you can't see from the figure is that the sample volumes are separated toroidally by about 20 degrees, but vertically only by about 10 to 12 centimeters here. And again, comparing the diagnostics is very useful because they have similar small spot sizes, and they're both sensitive to the ITG and the TEM, the long wavelength scales of the turbulence. And so we wanted to select for these comparisons a well-behaved, sort of very simple L-mode plasma that was MHD-free. So we produced a plasma with no SATI, there were no NTMs, and it's fairly steady sort of over this 400 millisecond region that we're going to be interested in for comparing the two fluctuating fields to each other. And we also have long time averaging, which is essential for helping us knock down signal to noise on these measurements. And so this is just very quickly the profiles in this sort of time period of interest, the plasma density, the electron and the ion temperatures, also the characteristic frequencies, and the optical depth of the second harmonic cyclotron frequency. This information here tells us that there's not going to be any refractive effects, no issues with the optical depth, so the temperature fluctuations we're seeing can be clearly interpreted as temperature fluctuations with no really contamination from density fluctuations. So we need to ensure that if we're going to be trying to compare the two fields, as hoping they are independent. And so what we found in these L-mode experiments, again, where the ITG is a dominant instability, is that the temperature and density fluctuations have very similar cross-power spectrum, shown here, the BES density fluctuations, plotted versus frequency in kilohertz, and the CEC electron temperature fluctuations shown here. And this measurement is made at about rho of 0.75. Again, scanning the diagnostics radially, we're able to build up information about the radial profile, and there we find that across the radius, these two fields are very similar in amplitude. So this tells us right there that depending on what the underlying phase angles are, here, because of the similar amplitudes, electron temperature fluctuations can be contributing at least as much as density fluctuations to the transport. And we wanted to take these measurements and compare them very carefully with nonlinear gyrokinetic simulations. And one of the things that we need to do there is we need to use synthetic diagnostics, which sort of mimic what the diagnostic actually sees in terms of its spatial resolution. So we've talked a little bit about, do simulations have the resolution we need to sort of capture all the turbulence dynamics? Even if we had the best sort of simulation with everything covered in the best resolution, we do have a fundamental limitation, which is even sort of the best turbulence diagnostics also have a resolution limitation. Because they're looking sort of at this background turbulent field predicted by gyro. Here are the temperature fluctuations and the density fluctuations at mid-radius. They're looking at this field with a finite spot size. And so what happens is you end up filtering, okay, you can't escape it, you end up filtering the amplitude of the fluctuation, sort of raw gyro at one particular time point in black, compared to the results convolved with a simulated spot size for the diagnostic, reduces the fluctuation amplitude, and also knocks off information at the higher frequencies. So this needs to be included when we start making comparisons between what we measure and what is simulated. And what we found is that in these plasmas, gyro tends to predict, which is consistent with what we see experimentally, tends to predict that the fluctuation amplitudes are very similar. And so shown here is just the fluctuation amplitude versus radius, pulled out the experimental data from density in blue and electron temperature fluctuations in red at just 2 radii, rho 0.5 and about rho 0.75 as an example. Overplotted on that are the density fluctuations and temperature fluctuations from gyro after the application of the synthetic diagnostics for comparison. And so again, it predicts the similar amplitude, consistent at both radii, but it cannot reproduce using traditional simulations that take experimental profiles as input. Simulations cannot reproduce the trend that the fluctuation profile should increase with radius. And so very extensive sensitivity studies were carried out, and this underprediction at rho 0.75 could not be resolved. So in flux tube simulations, you would go through, change the size of the flux tube, change how many k, theta, rho s you're sort of including up to. None of that really eliminated it. You could go in and start to modify the input gradients very slightly within error bars. That also wouldn't eliminate sort of this underprediction here. And so partially the radial trend can be recovered using gyrokinetic transport modeling, T-gyro, which I believe is similar to Trinity, which we will be hearing about more about that. But I think it's still not really clear what's going on at this outermost radial location in terms of understanding why we can't get the same kind of agreement here that we get deeper in the core. But so let's take for a moment then the simulation results here at rho 0.5. We'll say, yes, we know it doesn't work so well out here, but it seems to be working quite well here. We have agreement with transport as calculated using power balance calculations. We have agreement with 2 independent fluctuation diagnostics. Let's take those gyro simulations here and try to find out what else can we extract from them. Okay, what else can they tell us about the underlying turbulence? And maybe give us some guidance on what we should be trying to measure to sort of go deeper in our comparison. And so one of the interesting things here from this simulation that is working well, we find that gyro predicts that temperature fluctuations are driving the majority of the heat flux at mid-radius in this ITG L-mode plasma. So shown here is the predicted electron energy flux plotted versus k theta rho s. The total is in black, the contribution from electron temperature fluctuations in red, and the contribution from density fluctuations in blue. And so this disparity here, because the fields have the same relative fluctuation level, is coming in because there's some change, some difference in the underlying phase relationships between the density and the temperature fluctuations and potential. And so gyro shows that in these particular plasmas, the density and the potential fluctuations plotted here, the cross phase between the 2 fields plotted here versus k theta rho s, are out of phase. So you have non-Boltzmann electrons, you have finite transport, but it's a much smaller contribution to the transport here in that heat flux expression than the contribution from the temperature fluctuations and the potential fluctuations, which are very out of phase, shown in blue. And so again, we can't measure the phase angle between phi and n tilde, or the phase angle between phi and t tilde. But we hope to be able to extract this cross-phase information on the density and the temperature fluctuations, which is also predicted by gyro, using coupled reflectometry and CECE diagnostics. And that'll help us, give us one more parameter to hold up against the simulation and see how well it's actually doing at capturing the characteristics of the turbulence. And so along that path, we wanted to explore if we could sort of not just look at the static picture, this ITG-L mode, let's measure the cross-phase angle, we wanted to really push and say, well, let's measure the cross-phase angle, yes, in the ITG plasma, but let's also try and boost the drive for the TEM. Let's try and change the nature of the turbulence. And so we did this at DIII-D using ECH to modify the plasma profiles and change the drive terms for the ITG and the TEM instabilities. And so a series of experiments were conducted with these sort of similar parameters here. This is a pair of characteristic discharges. So what we did is we took that beam-heated L-mode plasma with profiles temperature, density, and ion temperature shown here, and the normalized gradient scale length shown here, and we then inject electron cyclotron heating. And so that gives us local heating, typically inside of about rho of 0.2 here, and that gives us a very strong increase in the electron temperature. It reduces the collisionality, so we can sort of boost up the drive term for the TEM. And we also tend to see that the ion temperature profile and ion temperature gradient are modified such that the ITG drive would be reduced. And so this gives us a very nice pair of discharges which should have sort of different turbulence characteristics to try and compare. So again, as we go from a really ITG dominant L-mode plasma, we add ECH to this beam heated L-mode plasma to try and produce something with stronger trapped electron mode turbulence.
I didn't quite see in the,
Yeah.
in the electron temperature profile, is one with beam only and one with beam plus ECH?
Yeah, so beam only is black and red is beam plus ECH. So they don't have matched input power. So in the experiment, we saw two very different responses again in the two fields to this change in the profiles. What we found is that if we look at the change in the electron temperature fluctuation level here measured at 3 radial locations as we go from the beam heated sort of ITG L mode to the beam plus ECH, so stronger TEM drive, we have this very significant increase of 50–60% increase in the electron temperature fluctuation amplitude. And in fact, at the innermost radial location, we were below the sensitivity limit in the baseline case, and sort of well above it here as we increase that trapped electron mode drive. And measurements with BES at the same radial locations showed little to no increase at the two outer radial locations, and in the core, very slight increases, maybe 5 to 10% here. And shown here, the cross power spectrum compared for the two cases, the BES beam only in black, neutral beam plus ECH in red, the same for the temperature fluctuation level. Changes in where the peak of the power spectrum occurs and also how wide it is, those we relate to the changes in the Doppler shifts in the two plasmas. But the integrated fluctuation level, again, for the BES is about 1.2% at rho of 0.7, so very little change. In contrast, the temperature fluctuation level, very significant increase. So this different response was very intriguing because imagine if we didn't know what the temperature fluctuation levels were doing, we would then have an experiment where we've significantly changed transport, but we saw no change in the density fluctuation amplitude. And that would sort of be outside our standard picture of what should happen. And so it was the inclusion of this temperature fluctuation information that said, well, wait, okay, you have the change in transport, and now here this other field is sort of changing the way you might expect if these fluctuations are driving that transport.
Do you know why there is a shift in the second spectrum for density and not so much for temperature?
One of the things I thought here, so why there isn't a shift in so why there's a much larger Doppler shift apparent in the density fluctuations and less so in the temperature fluctuations. I think two things there. One thing, I think we might be sort of up against a noise limit here in the beam only case, so we might not have sort of enough well-resolved spectrum up there to see the shift as strongly. And also the BES is slightly more sensitive to higher K. And so even for the same sort of E cross B flow, you get a larger shift there. So those are the two things there that I've sort of thought might be going on.
And
Yeah.
the black curve could be underestimated, right, for delta T over T, if some part is...
Yes, that's right. That's right. This is all in a specific frequency range where we make the fluctuation level comparisons. You know, we choose the same range for both sets of diagnostics. So we cut off we cut off the information at the lowest frequency, so we only go up from maybe 40 or 50 kilohertz up to 400 kilohertz. So yeah, that's right. The fluctuation level is dependent on which frequency range we select for that analysis. Okay, right. So this was sort of the change in the two fluctuating fields, and we want to look now at what gyro is also telling us should be happening to the change in the phase angle. And so what we did is we used gyro to predict what sort of change in the NT phase angle we should expect as electron temperature is increased by changing the inputs to gyro the same way we change them with ECH in the experiment. And what we found is that in these gyro runs where we increase the trapped electron mode turbulence in this way, gyro predicts several things. It predicts an increase in heat transport, was consistent with what we found experimentally. It predicts the very large increases in T tilde, 50 to 60%, predicts more moderate, smaller changes in N tilde. Gyro actually predicts maybe 30% and measured is maybe less than 10%. But that's roughly consistent with what we're seeing in the experiment so far. And now gyro also predicts this increase in the N5 phase angle. So even though gyro says the density fluctuation, so gyro tells us then that the transport is changing and it's related to these two things. Increase in fluctuation amplitudes and also this underlying change in the N5 phase angle, okay? With no change in the underlying T5 phase angle. And so what gyro shows us we should be able to measure in terms of the cross phase between density and temperature fluctuations, if we look at the base case in solid and then compare it to this high TE case with the stronger TEM drive, we have a reduction in the cross phase angle between the density and temperature fluctuations. And if we can increase the electron temperature sort of percent-wise, we can watch that cross phase angle decrease. And so then in the experiment, we should expect to measure a reduced cross phase between the density and temperature fluctuations in the plasma with the ECH compared to the plasma without. And in fact, that is what we found with the experimental measurements. And so very quickly, the way that the measurement is made is with a coupled X-mode reflectometer and the correlation ECE system. So they share an antenna and they view the plasma along the same line of sight. And so this allows us to overlap their sample volumes radially by selecting which frequency the two diagnostics look at, and the shared optics allow us to overlap the sample volume poloidally and toroidally as well. Okay? That's to be contrasted with the BES comparisons where the two systems are independent and their sample volumes are separated vertically and toroidally. Here, they're coincident, and the spot sizes are similar. So we're looking at long wavelength electron temperature fluctuations with one of the CECE signals, and we're going to correlate that with one of the X-mode quadrature reflectometer signals, which is sensitive to the long wavelength density fluctuations locally. And that's going to be giving us the information about the cross phase between density and temperature fluctuations that we can extract from the cross power spectrum. And so here are the actual measurements from the experiment shown at 3 different radial locations, rho 0.55, 0.65, and 0.75. Plotted here are the coherency between the density and the temperature fluctuations and the cross phase angle. And so at the 2 innermost radial locations, we do find that the cross phase is reduced from the base case shown in black to a much smaller phase angle in the high TE cases shown in red. That's qualitatively consistent with the trend that we expected based on the gyro simulations. But interestingly, at the outermost radial location, we find that there's very little change in the cross phase angle. Okay? And so we're not sure why this necessarily should follow this trend, because again, the gyro simulations we ran were for the core, and we know gyro has difficulty predicting what's happening at rho 0.75. But also, at these 2 measurement locations, there was very little change in the E cross B shear. But at this measurement location, there was a much larger change in the E cross B shear, which might also be impacting and affecting the cross phase angles. And so we've also gone ahead and with synthetic diagnostics started to compare quantitatively the measured cross power spectrum between density and temperature fluctuations and the measured cross phase angle between the density and temperature fluctuations, experimental values shown in blue here, with the gyro simulations. And this particular simulation case is from about rho 0.65, and it's for the high TE case only, so it's going to be the strong TEM drive case. And what we find, interestingly, is that we can get good agreement within the experimental error bars of the experimental density and temperature phase angle and the gyro predictions. But interestingly, what we found is that although we see that the shape of the spectrum predicted by gyro is very sensitive to the size of the spot size that we use, and that we know from our past experience with synthetic diagnostics, that again makes sense. We don't, however, find that the phase angle is sensitive at all to the size of what the sample volume is that we use in the modeling. However, the cross phase angle will depend sensitively on the spacing between the CEC and the reflectometer sample volumes. So we can pick up errors there because our mapping there is going to depend on the density profile for one. And also, we need more modeling of the reflectometer data to help us understand what's going on here, okay? The fact that we see the correlated density and temperature fluctuations tells us that we have radially localized measurements of the density fluctuation amplitude from the reflectometer, but we also need to make sure that the phase of the underlying fluctuations, okay, in the reflectometer signal are the same as the underlying fluctuations in the density turbulence. And so this is sort of the newest measurement, and it hopefully will be able to give us a lot more information about the turbulence and help us do more critical comparisons against the theory and the simulations. And so just to sum up, we found, interestingly, in ITG-dominant L-mode plasmas that long wavelength temperature and density fluctuations are very similar in amplitude to each other. We find that after the transition from L mode to H mode, an improvement in confinement comes along with a reduction in the amplitude of core electron temperature fluctuations. We've also performed experiments where we've increased the trapped electron mode drive, so we increased the transport in the plasmas using ECH, and we found very different responses in the temperature and density fluctuations, very large increase in electron temperature fluctuations, much smaller increase, little to none in the density fluctuations. And gyro simulations predict that these increases in transport as the TEM drive go up are associated, yes, with the change in the fluctuation amplitudes, but also with the change in the underlying cross-phase angle. And while we can't get at that, using the new coupled measurements of the CEC and the reflectometer diagnostic, we're trying to get at the changes in the density and temperature fluctuation phase angle and comparing this with the predictions from gyro. And there again, we have an ongoing modeling effort. So thank you very much for your attention.
Questions?
I think it was in your slide 14 or so when we showed some temperature profiles for the electrons and ions.
Mm-hmm.
And it looked to me like the electron temperature gradient was actually higher than the ion temperature gradient. So do you know how deep you are into the ITG regime, or could you be close to a transition between ITG and TEM?
Yeah, we could be close to a transition between the ITG and the TEM. Looking just at linear stability calculations from TGLF for this particular plasma, here it looked like we were fairly deep in the ITG range. But when we went and did the second set of experiments where we had the two different plasmas, this L mode, it wasn't quite the same as that other L mode. We tried to make it as close as possible, but we couldn't. That first one was a diverted plasma, very strong in the ITG range. This one was inner wall limited. And there the linear stability calculations show it's a little bit more towards the TEM range of things.
But it should be still ITG according to your...
Based on that still ITG, based on the nonlinear simulations as well, sort of in the ITG
And when you
range.
say that your H mode is also a suppressed ITG mode, so I suppose you have done also calculations, these linear calculations that show that ITG modes are the most unstable?
Yes, for the well, maybe Lothar could say more about that for the QH modes.
In the higher density H modes with the flatter gradient, yes. And then there's other cases where there's a larger electron temperature and density gradient where it's really TM-like in H mode, at low collisionality especially.
So it could be both.
This H mode here that you showed is actually a pure H mode. It's a low collisionality.
Yeah, that's like 125113, that one. So
Right, yeah.
yeah.
And how do you understand the increase of the fluctuation amplitude, which is quite substantial, right? It's a factor of 3 or so over a quarter of the radial domain. Do you have any qualitative understanding, at least, where this comes from?
For why the fluctuation level is increasing with radius? I mean, I've seen some of the simple explanations where you just have increased gradient drives. You could plot all of these versus some sort of respective driving gradient. You could plot them all versus A over L and E and A over LT. They all scale with that, right? I mean, that you will see as you plot these data versus the gradient scale length versus radius. But what I didn't show here were some experiments that Jim Debou did where there we're relying on the variation in radius to give us this change in, say, A over LTE. But he did experiments where he locally modified the A over LTE drive to try and push from ITG into TEM. And I think, Lothar, do you have some results from Jim's experiments? Or
I'm not sure whether I don't
Terry
have
does? Oh, okay.
Not Jim's experiment.
All right.
Don't have time.
But there you see as the drive goes up, generally you see the fluctuations respond as expected, although there were some surprises.
Back first.
say that when you go from L to H mode, you see this big change in turbulence quite deep into the core.
Yes.
So that means that besides of gaining your pedestal, you also gain a lot of extra confinement in the core. And do you see like a change in your critical gradient? Do you get steeper ion temperature profiles?
I don't know off the top of my head what the critical gradient estimates would be for these plasmas, but it's definitely, but the important thing to note is, again, this reduction here in the core plasma compared to the edge is not happening as quickly. Okay, the reduction in the edge happens very fast, sort of tens of microseconds. Here, it's happening much more slowly. I mean, the time resolution of the diagnostic is maybe only 50 milliseconds here. And so we can say that these changes are related to the change in the gradients in the core.
So my question is about the spectral comparisons between the diagnostics and the gyrokinetics using what you call synthetic diagnostics. So this is taking account of essentially the spatial filtering that comes from finite volume size. That spatial filtering, or that volume size, is translated into a spectral shape of smoothing by essentially the Doppler effect, how fast the plasma is rotating. So the question is, how fast did you take the plasma to be rotating in your comparisons with gyro, since that number in the simulations is essentially arbitrary?
We took here the calculations, the numbers based on the CER measurements from the radial
You
electric
take the
field.
experimentally measured
Yes.
ER
Yes.
and you apply it to the gyro simulations.
Yes, that's right. So we don't have, none of these gyro simulations were for cases where we didn't have the CER measurements. So we were never allowed to arbitrarily put it in. We had some measurement information, but there are large error bars there. That's one of the uncertainties that can contribute to sort of how well we think we're getting this comparison between the measurements and the simulations, because that spectral shape is very sensitive to that value we put in. And also the amplitude of the turbulence would be very sensitive to the value of the E cross B shear. So both of those things are essentially knobs that one could vary within error
Well,
bars.
my question was about the value of ER rather than about its shear.
Well, for this particular comparison, it's exactly what we said here. There's no fiddling. It's just taking directly that measured value, okay, and saying that's what we think the Doppler shift should be. But as you can see, it doesn't reproduce the shape of the spectrum in this case at all. The unfiltered does a better job than the filtered. And so that could be attributed just to the error in the ER you put in, but there could be something deeper there.
Those are simulations with shape.
Yes.
There are some subtle, I just comment that, but there are some subtle differences in the spatial characteristics that might account for that. I'll show it here.
Correct. Changing ER is going to stretch out that red curve left or right, but it's never going to give a valley at low frequency.
Right. That's also something that we see in these simulations and also in the many simulations that were done on the other ITG Elmo case. There always seems to be sort of more fluctuation power predicted down here at the lower frequencies than what we see with the diagnostics. I think that's true also when we do the spectral comparisons with BES. So, yeah. So there's a lot of, I think qualitatively things are very interesting. There's a lot of compelling consistency, but I think when we look deeper quantitatively, there's a lot of effort required to make sure we think it's really doing as well as sort of the preliminary qualitative look suggests.
Greg, why do you say can never produce a valley?
Changing ER is just changing the Doppler shift, so it takes that spectrum and stretches it out.
So yours is a theoretical statement, which is that there is never a low frequency valley in the turbulence.
Mine is a mathematical statement of how you translate the gyro results, which are in the plasma frame, to this, which is in the lab frame, which is Doppler shifted. So you take the gyro simulation. Okay, there's a subtlety in that even in the lab frame, there's a finite frequency spectrum. So
yes. Yeah.
But my other question was about the phase shift. There is, to get a net heat flux, you need a phase shift between, if things were exactly Boltzmann response, as Steve wants me to call it, temperature and potential What?
Don't listen to him.
Temperature and potential will be exactly 90 degrees out of
Everything's being
phase.
recorded.
Or temperature and density would be exactly 90 degrees out of phase, and there would be no net heat flux.
Exactly, right.
And so theorists talk about some kind of an average phase shift with some weighting over the spectrum. But here, I'm just wondering how you define the cross phase angle. That might not be the same. Is the synthetic diagnostic being used to calculate this cross phase from the gyro in the same way?
The same way we would do in the experiments. So we use the synthetic diagnostic to filter the gyro results to basically produce a time series, which should then have the right sort of spatial response, like the diagnostics. And we then do FFTs on that, calculate the cross power, extract the cross phase from the cross spectrum. So yeah, so it's not as if we've done the calculation of the phase angle versus k theta rho s and then tried to average over some k theta rho s. I mean, you could plot that and look at that and analyze it, but that has not what's being done here.
So if I'm understanding what you're telling me correctly, numerics allege more fluctuations at lower frequencies, right?
These simulations, yes.
So I guess the first question is that, does that mean that they're also longer scale? And secondly, this, if that means that, right, that would presumably mean that the numerics overestimate transport.
Yes, and they do in this plasma. They're overestimating heat flux, I think, by more than a factor of 2.
Are these longer spatial scales as well as lower frequencies, or is that not as straightforward?
I think that's not straightforward because we have to have the wave number spectrum measured in the experiment. And BES might have some information about that, but I don't know off the top of my head if that's something we also saw in these particular plasmas or not.
How generic a problem is this? Is this just here, just now that this has happened, or is there some genericity to numerics picking up?
It's generic.
serious
It's
low
generic
frequency
to the
stuff?
simulations that I myself have done and simulations I've seen that people have done of these types of L-mode plasmas. I don't know if that means it's generic to simulations done for other experimental conditions on other devices. I don't know, but it's generic to what I've seen, at least for trying to simulate these types of plasmas.
I'm sort of, I'm very tempted to say that if you under-resolve things in velocity space and in the parallel to the magnetic field direction, you may pick up spurious inverse cascade. Because your system is going to think it's 2D, while it actually isn't. At which point you're going to be pumping energy into lower wave numbers.
Mm-hmm.
It could also be a marginal stability thing. That, if you were to raise the E cross B shearing rate or somehow reduce the temperature gradients a little bit to move close to marginal stability, it would be mostly the long wavelength modes that would get suppressed first.
Yeah, but you need to be really careful jumping into over-interpreting this because, for example, when you're using reflectometry, you don't know how its sensitivity varies with K. It probably decreases for the long wave number modes, so you need to be a bit careful about the experimental side of things.
Yeah, and
there's
that's
a good reason why that's arbitrary units. I mean, it might actually be arbitrary in spectral shape as well to some degree.
I think that's
You've got to defend yourself.
No. I'm going to agree with that. I'm going to agree with that, right? Because all we tell the gyro simulation is that basically there's a high K cutoff. There's a high frequency cutoff. We haven't incorporated into the synthetic diagnostic any type of low frequency or low K cutoff into either the modeling of the reflectometer or the CEC system. That's right. No, so that's totally fair. I mean, again, the modeling here is quite simple in that sense. So if you tried to get out a better sort of picture of what that spot size was and what the K response was, again, you might have a better quantitative result. And so it's not just fiddling the input profiles, it's also trying to adjust the parameters on this synthetic diagnostic. So it's good because it can help you, try and understand the comparison more, but, it's also bad because there you're introducing another uncertainty in how well you model that response.
So thinking ahead, maybe this is one of those things that we should try to nail, whether the low frequency stuff is simulation.
Full wave simulations to figure out the electron response, presumably.
We benefit from all of that.
How nonlinear is this cross phase? I mean, you're doing nonlinear gyro simulations, but if you just were to predict it from linear theory?
For a particular set of plasmas, when the base case is strongly this ITG case, all right, compared to the case where we might be more mixed. As we increase the TEM drive, what we find from the linear simulations versus the change in electron temperature fluctuations is the linear simulations in blue track the nonlinear simulations in red. And this is not averaged over K. This is at a particular KY, K theta rho S of 0.2. But what's interesting about that is these cases we used to make the prediction ahead of time had this very good agreement between the linear crossphase and the nonlinear crossphase. But when we did the nonlinear calculations for the actual experimental discharges, there was disagreement between the linear and the nonlinear crossphase. And I think that might be attributed to the fact that we have a much stronger A over LTE, a much stronger temperature gradient drive in the actual experimental conditions compared to the parameters we used for the gyro simulation. So that might be related to this breakdown between that linear theory and the nonlinear theory. But again, that's why I think the phase angle in particular might be very helpful for helping us validate full nonlinear simulations, but also the linear and quasi-linear simpler transport models.
All right, I think we should move on. Let's take in once again